So, very good evening to all of you. I would like to welcome all of you to today's session of Systems Engineering Application Program in ITSM Dhanbad. So as you have already seen in the part one of module 3, that what are the input and outputs in a system and how the system representation happens, right? So in the module 3, the next part I am covering, that is the system representation, or you can say that the simulation of the system or replication of the systems. So here I'll be covering the system simulation part, and though there are several simulation models in research and in other practices, but I'll be covering the system dynamics modeling, which have been developed precisely to understand the dynamics of a system. And system can be anything, as you know in advance, right? So what is simulation? Simulation name itself suggests that something you are trying to simulate, right? Where the features are similar, but things are not happening in reality. We are just developing some virtual models, and where we try to replicate our understandings so that the multiple domains or multiple angles we can study in the simulation models, because many things we cannot study by doing in reality, right? So we have to analyze the system, and we will be doing it through simulation. So simulation is a virtual model of a real system, right? Then simulation model helps to understand the system's behavior, and it includes all the parameters which are required or which supports in a system. It may be subsystems, components, subcomponents, elements, or it may be just the external factors through which the system is getting impacted or its performance is getting changed, right? So those factors we'll be considering to cover the overall system performance. Then the simulation models. These models basically replicate the real-time relations, and this helps us to bring out the correlations among all these parameters which are the part of a system, right? So system simulation models basically consider the variation of all the subsystems, components, subcomponents, and the elements involved, right? And some variables may be changing with time, some factors may be constant with time, but even then there will be some impact of those constant parameters. Then there may be a possibility that after certain intervals, some parameters are changing or some behavior is changing, right? So different kind of parameters and different kind of patterns involved. So in systems simulation, we try to bring insight from all these angles. See, in reality, it is very difficult to understand that how things are working, right? How exactly within this particular time interval, if this value is changing, how it will impact to the overall system's behavior. So in reality, when the things are operational, it becomes very difficult to understand that exact impact. So we develop the simulation models to uncover the details of the systems. System dynamic modeling. System dynamic modeling is one particular methodology which has been developed for to understand the system's behavior, right? So here in this particular modeling process, we will be simulating some real-time systems, and then we will be understanding how the parameters. You see, in when I'm talking in the class, let us say it's a air conditioning system, right? It's a small system, right? And now if I would like to understand that how the current is impacting its behavior, then maybe the fluctuating voltage, how it is impacting the performance of this air conditioning system. Or you may just imagine that the external temperature, will it be impacting to the performance of my air conditioning system? Yes, there may be. But you see, these are just some parameters I counted to understand the behavior of a small system. Now you imagine that when you are trying to understand what parameters are very critical and what parameters are important to investigate more to improve the system's efficiency, then we need to bring all these parameters together to uncover those insights, right? But the question is, when you are doing the modeling, some mathematical relations are required to be expressed, right? And all those parameters will be related through mathematical or maybe physical expressions or physical relations might involve, right? So this is how we have to understand that how the things are happening in the systems, okay? Then you see system dynamic modeling. Systems, the worst thing is system. Though by now we have talked much about system, but once again to recap, systems thinking opens up our visualization to understand the exact location of a particular subsystem or a particular component. Remember the togetherness, the assemblage, and then the acclimation, and then there were other parameters which define the systems. And when you have the systems thinking, you will be not having any individualistic thinking. You will be having a thought of overall systems performance. Or if I switch off this air conditioning system, how the other components will be behaving. So that kind of understanding we have to take up, and the system simulation helps us to keep having the thought of systems thinking, right? Then dynamics. Dynamics, as I told you, that every system's performance may change with the time, or maybe some parameters, right? If I change the voltage, there may be a problem with the functioning of the air conditioning system, right? Or there may be, if I change the volume of my mic, or if I change the screen setting, there may be a problem of of overall efficiency of the overall system, right? So that is how the dynamics is. The dynamic term is helping to reveal that how the changes are happening in the system, different parameters and different time instances, right? So this is how the things will be changing. Then you see models. Models can express the mathematical and physical relation through simulation to replicate the system's behavior and changes with time and related variables. Moreover, if you try to model a system, it is usually very important to break the system into small parts, smaller components, right? Once you have all the subcomponents, all the subsystems with you, then it becomes very easy, right? Very easy to understand that what are the primary impact factors, right? Then you may say that the systems simulation models cover all those variations in detail. So that becomes very important to understand that how these particular parameters are related. Simulation itself is defining that you are replicating. So replicating means the way the components of a systems are related in reality, the same way it should be related in the simulation model also, right? Then the very important parameter is that how the changes are happening with the time. So let us say for one particular set of parameter values or systems stages, there may be a different performance of the overall system. After some time, maybe after one hour, if I change the combination of all the parameters, there may be a possibility that the system's performance may be different now. Likewise, with the time, if I am changing parameter values or subsystems performance, then the overall system's performance may be changing with time. So that insight actually help us to understand that exactly what parameter is giving the highest impact, or exactly what parameter is there which is giving the minimum impact, or with time how my system is performing. So several kind of insights we can get in the system dynamic modeling. So let us go in detail now. System dynamic. So system dynamics is one type of simulation based on mathematical interrelation of all the subsystems and elements of a system. Then system dynamics is basically a technique which brings the insights about how these things are interdependent, right? Or which kind of input one component is providing to the other component and how they are related. Means if one is increasing, does the another will also increase, or do they have any direct or indirect impact on the system's performance, right? So those things are required to study. Then the behavior of the system's components. These determines the system's overall behavior, and systems engineer identifies the loops. Loops means the interdependency of the parameters, right? So there may be a possibility in the information input output flow that some information is getting into the system and some information is getting processed and becoming an output. And now this output may be behaving as an input to another component, and again you may receive some information back to the previous element, right? So that kind of feedback loop may be existing in reality. Then the causality. Causality means if I vary one parameter, how will, if they are related, definitely there will be a change in the second parameter. So if I increase first parameter, what is the impact on the next parameter? Increasing, decreasing, or what else, right? Or maybe constant, right? So that we'll try to look into the particular systems model, right? Now the technique. So the technique, if I talk about, you see, system dynamics modeling is basically proposed in 1950s. It has been proposed by J. Forrester. And then you see the system dynamics modeling have been proposed particularly to uncover the details of a system, right? With the systems thinking thought. There may be some internal parameters, external parameters, and then we'll be discussing or trying to understand the overall behavior, right? So in this, it becomes very important that why this particular dynamic modeling has been done for any particular system. To understand the system dynamics, many students get confused that is it a dynamic simulation or system dynamics. So I always rectify them. You see, dynamic simulation always helpful, but it basically helps in dynamically understanding that how the machines or how the systems that engineered systems are behaving, their particular functionality where all the components are involved, just the system. But when we are trying to understand the system dynamics, it includes several other parameters. And this system dynamics modeling is not only focused on the engineered systems, however, it is focused on the organizational systems, the process systems, engineered systems, everything. It can be applied anywhere. And in this particular system dynamics modeling, we do not only consider the technical components, while in the dynamic simulation particularly, we consider only the technical components will be considered to understand the dynamics or the behavior of that particular product, right? But here in the system dynamics, any systems dynamics can be understood. And it involves not only the technical parameter, while the external parameters and other kind of possibilities. Let us say some organizational parameter may be impacting the performance of my equipment, and that also can be considered. So here, the system dynamics modeling consider the systems thinking approach, and where the broader categories are all involved in a system. So we'll see some models slowly, and then you'll be understanding better, right? So the very first research using this system dynamics model was developed to address the bullwhip effect in the supply chains. This system dynamics modeling is really a powerful tool even after 75 years, right? Though there could be, a lack of use cases, a lack of case studies were there, and it is not the because as I told, systems engineering itself is a domain which is really less popular. But in practice, everybody is a systems engineer. Whether you have done electrical engineering, mechanical engineering, electronics engineering, or whatever, right? But at the end, everyone is performing as a systems engineer. So those who are the practitioners here might be able to relate my thought here very clearly, that it is not only your electrical knowledge required. Slowly, as you are growing up in any organization, you may be required for multiple domains, and you have to understand the multiple facets of a particular product or your organization, right? And there you may see that how the parameters are interrelated, right? So this is how, in this particular system dynamics modeling, we'll see that how the system dynamics modeling uncovers the critical elements in the system and identify that which parameters are helping to improve the system's performance and which are the parameters which are reducing or negatively impacting the behavior of the system, right? Then the system dynamic models help in decision making. What kind of decision making? To improve the performance. That is the only motto, right? That's the common goal to everyone who is working in a system. So, whatever are the hurdles, bottlenecks, this helps to understand that what are the bottlenecks to my system's performance, right? Then, with this particular insights, you may work on the to improve the policies, improve the processes, and then accordingly you may find an idea that how to develop more products or different other processes, right? So this will how you will improve the particular system overall. Then the two type of models will be seen throughout the session today. One is causal loop diagram, and the another is stock and flow maps, right? So when I'm talking about causal loop diagrams, it is very clear. Cause loop, it means there is some causal relationship and then the feedback loops may be existing. Then the second will be stock and flow maps. Stock and flow means stock is very clearly, name is itself explaining that something is accumulating, some stock is there, right? And then the flow means somehow some rate is there to reduce or increase that particular accumulation or particular stock. So these two terms are the major terms which we define in our models, and with this we'll be able to get some insights in our systems. Then what type of variables exist in a system, right? What kind of variables? So one is endogenous and the second is exogenous. Endogenous is very clearly, I think the name is itself satisfying that what do you mean by endogenous and exogenous. Endo means depending on internal thing, exo means depending on external. So it is endogenous variable is a dependent variable which is dependent on the variables within the system, right? And you can say it's a dependent variable. Somehow it is getting impacted by the variables which are within the system. When I'm talking about exogenous, it is a kind of independent variable or external variable which is impacting my system's parameter or system's factors, right? It's a kind of parameter or kind of component or variable which is not generated within the system elements, that is controlled by external factors, right? And these exogenous variables usually impact the endogenous variables. So that is why these exogenous variables are called independent variables, while the endogenous variables are called the dependent variables, right? So now moving to the next slide, association of variables in a system, how these variables gets associated in a system. System structures, as you already know, that made up of several variables. Some may be impacting positively, some may be impacting negatively, but they will all be, connected with some arrows. And over the arrows, we'll define the causality, polarity of the relationship. Let us say one parameter is related to another, but we'll be writing a polarity sign, or you can say how this link is behaving. So to understand, many times, researchers say that they both are moving in the same direction, means one is increasing, other will also be increasing. So they put a sign S over the arrow. And some researchers present that with a plus sign, it means one is increasing, so other will also be increasing, right? So this is how different parameters or different representations are there in the system dynamics modeling. And these endogenous and exogenous variables will be related by the loops, or there may be positive or negative feedback loops. Closed systems. Yesterday only you studied it. Closed system. In how the closed systems behave. Closed systems itself is defining that there will be a information will be going back to the initial point, right? So this particular feedback loop exists in the closed systems, and input may be affected due to the change of output. So there is an interdependency, and this kind of cyclic effect will be considered in the system dynamics modeling, right? Then the feedback concepts of is originated from the control theory. Again, there is a lot of mathematics behind these concepts, that how exactly those parameters are related, right? So this is how a causal loop diagram depicts the visual interrelations of elements. So far we have seen what are the variables, how they are linked, right? Then now we will be seeing that what are the causal diagrams. Causal diagram is something which is very common in different other studies as well, right? Causality is something which defines that how the output of the first or one parameter is impacting the output of the second parameter, right? So the causality is something, the cause is required to be defined, and the effect also requires to be defined. So one kind of causality is positive causality. Positive causality can be represented like this. You see, A and B are the two components of one system, two components of one single system. And now A is causing the occurrence or causing the behavior of B. So there different interpretation you can make of causal relationship. So causal relationship in itself explains that one is cause to impact the behavior of some particular component, or you may say that one is originating the other. But in case of system dynamics modeling, we say these two parameters exist, but how they are related. So this relation is positive, it means the polarity is positive, it means when A is increasing, B will also increase with A, right? So this is how they are dependent on each other. If A is with respect to A, B will be showing positive changes or in the same direction of A. If A is increasing, B is also increasing. If A is decreasing, B will also decrease, right? So some researchers express this plus sign with no uh, with a particular S symbol that shows the similar behavior, or if A increase, similarly B will increase, right? And one very important thing to notice here, you see, in this particular relation, if you see A and B, they are positively related, okay, moving in the similar direction, fine. But now the question is, if at all I am saying there are 1,000 parameters in the system which may be impacting B. So how are you so sure that A and B are moving together or moving in the similar direction? That is actually the major takeaway from system dynamics modeling. Because you may say that, let us say B is increasing today, so B may be increasing by due to the change in A, maybe due to the change in C or change in X, Y, and Z parameters. So how do I know that exactly A and B are moving in the same direction? Because we are capable to perform the sensitivity analysis in the system dynamics modeling. Where what do? We conduct a kind of analysis. We say that if I keep all the variables constant, right, and I just try to check the effect of just one parameter on this particular B. So in this case, let us say B is depending on B, C, X, Y, Z, four more parameters. So what will I do? I'll say keep those 5 variables constant and change in A, and then you see how the system's performance of B is changing. So this is how we'll able to analyze and we'll able to identify the right polarity or right relationship of causality in the system, right? So this is how we have to perform the sensitivity analysis to understand the exact relation of two parameters only. While it is very clear A is also dependent on multiple parameters, B is also depending on multiple variables, right? So exactly identifying the exact relationship of A and B, it is very clearly shown that it can be performed using the sensitivity analysis. For example, when A and B are positively related, what kind of examples? Let us say product cost and product features. If you keep on improving the product features, definitely the product cost will be changing, right? Or you can say increase in the product features will increase the product cost, right? So these two variables will be moving in the similar direction, right? So these kind of causal relationship will be existing between these two parameters or these two variables, right? Now next example, if a company offers that the after sale services are very good, other company is giving just 1 year of warranty and this company is giving you the 10-year warranty. So definitely customers will be moving to that particular company which is giving the warranty of 10 years. So definitely after sale services are better. So better will be the customer base, or increasing the after sale services, it will be increasing the customer base, right? So this is how these two variables are positively related, right? And somebody may be, asking that exactly you are defining the positive, okay, fine. But there will be a mathematical relation also. We'll be expressing an equation as well, that how exactly customer base is depending on what parameters, linear or quadratic or whatever changes you would like to include. So one statement I make usually in my all classes are related to systems engineering. More you know the system, better you will be able to model it, because systems parameter, identification of the systems parameter is itself a task and which comes with the experience. So that is the reason why we consider the experts input in this particular system dynamics modeling. How will you identify the components, the subsystems? Those who are the researchers here might definitely be having a query in their mind that how to do, what to do, and how to start. So let us say if you would like to understand a system, maybe a supply chain management system of a particular company or a particular, let us say, food supply chain, right? So because you are not working in that particular domain and you are the just a user, right? Or you can say you do not know the exact components of the supply chain or exact parameters on which the supply chain performance depends. So in that case, you have to review the literature, right? You have to identify the experts who are working or who are having an immense experience in the kind of food supply chains. So if you are having that particular connect, then only they will make you understand that how to improve the particular system, right? So then it will become very helpful to you that how exactly things will be done. So this is how you will get the exact list, and then slowly I'll be evolving with this, and you'll understand that how you can apply in your research. Okay. So this is one kind of positive causality that you have defined here. Okay. Then I'm going to the next type of causality, that is called the negative causality. How the two parameters are negatively related. So you see G and E, two parameters are defined, and it is saying G is impacting E negatively. Or another way to understand is, if G is increasing, E will be reducing, right? So link polarity is negative in this case. Negative in the sense, we'll clearly explaining that one variable G and other variable E are going in the opposite direction. If G will increase, E will decrease. If G will decrease, E will increase, right? So this is how, with respect to G, E will be keep on reducing. So you see, by fixing all other variables, it means I'll make the other variables constant, and then I observed that how this G is giving an impact on E, right? And I found that if G is increasing, E is decreasing or diminishing. So this is how we can clearly understand and clearly uncover this relation when things are happening in reality. As I few minutes back, as I gave you an example of air conditioning system. So if I say the voltage is changed, let us say somehow the AC is not working today. It has stopped working. And now whomsoever is the repair person for this particular air conditioning system will come and will test everything. Why? Because the overall system's performance got stuck, and that for that multiple parameters are there within the air conditioning system on which its performance depends. So it becomes sometimes very critical to understand which parameter is not working well, or which parameter or which variable is actually creating the chaos, or not, the system is not at all working. In the same way, if I consider an organization, right? Let us say one student has done something which is not not in favor of other students, or which is not favored by the in the academic system. So then what will happen? People will be, or if I say a performance of a particular team, if a team's performance is impacted, so what we will do, we'll just immediately try the team's performance is dependent on what parameters. And if any of those parameters is not properly properly aligned, that is the reason why team is unable to perform, right? There may be some clashes with the among the team members. There may be some instruments may not be working, there may be some official issues, there may be some different kind of technical issues, there may be several issues. But what exactly, let us say there are 5 parameters which are impacting to a system, right? So for me as a systems engineer, it becomes very important to understand that what exact parameter is there which is giving the highest impact, right? And that I'll put it into the critical domain, and then I will say, okay, fine, this is the most important element which is giving the highest possible impact to the system's performance. So I'll keep monitoring that particular variable. So this is how we always get insights that what is positive related, what is negatively related. If my system's performance is dipping down, I'll immediately catch those factors or catch those variables, and will try to stop or somehow make those variables constant, or remove those obstacles in my system, right? So if I see the examples of negative causality, so for example, if the product prices are increasing, sales will be decreasing. Simple example, which you have seen in many of the cases, right? One more example, if your workload is increasing, your work quality may be impacted. If your workload is on the middle level or little lesser, your work quality may be improved much, right? So these are some of the examples how the negative causality works in the system. Then the causal loop diagrams. So far you see we have seen the negative and positive causality, but now it is just one way, right? But now we will be understanding what is the causal loop diagram. So in the causal loop diagrams, again, when the feedback loop is coming back, it may be giving the positive input or maybe negative. So again, the causal loops are also of two types. One is positive feedback, or you can say the reinforcing loop. So let us see that what are the reinforcing loop. So you see R is expressing the reinforcing loop. Production is increasing, right? You see here, production is, if you increase the production, definitely the inventory levels will be increasing. If the inventory levels are increasing, it means you need to, the production will be keep on increasing, right? So increasing inventory levels will be increasing the production or impacting the production. That production output is increasing, so you should produce more, right? In the same way, we can have one more, example: rainfall and the average crop production, right? So in this, you see, when you're talking about one particular, kind of things, you see something missed out actually. I was talking about the positive feedback loop. Yes. So you see in the positive feedback loop, we talk when the production is increasing, inventory is increasing, and if inventory is more, production will be more. If inventory is reducing, it means production will be reduced, right? The same way, if you see rainfall is increasing, so average crop production will also be increasing. It is just a mental model, right? It is a thought, and it is a systems thought basically, and we are just trying to understand whether my hypothesis or my understanding about the system is correct or not, right? So that we'll run in a system, and then we'll try to understand that what I was thinking as a systems engineer, that this particular variable is impacting positively. So now I'll test all those hypotheses or all those mental models in form of these feedback loops. So positive means, it rainfall is giving the positive input to average crop production, and if the average crop production is increasing, it will attract more rainfall. So again, it will be going back positively. So this all, if you see, the whole loop is giving the reinforcing. One is increasing, other will increase, and if other is increasing, again it will giving a feedback of increment. So overall, it will be called a reinforcing loop, right? So in this particular positive feedback loop system, we have seen that how things are. Now in the negative feedback, you see at one side here, you see in the negative feedback systems, what is happening? This is called balancing loop. Why balancing? If you just imagine, the very important point to notify here, if you do not put the negative feedback loop, so can I say the inventory will be keep on increasing forever? Or if the average crop production will be keep on increasing forever if the rain is increasing forever? But what happened in reality? That these are not the just two variables which are interrelated. There are 1,000 variables in the whole system. So what happens in reality? Some are positively interacting and some are negatively interacting. So the overall system will never be kept on increasing all the time, or never be kept on decreasing all the time. So the overall system's performance will be increasing or will be better for some time. Then the other factors may come into the picture, and then they will reduce the system's performance. And then again the positive feedback loops may come into the picture, and the system's performance will be increasing. So like this, there will be an oscillation of a real-time system. It is not just the, so now we are just seeing the overall impacts, right? Because it's a brief session on system simulation. Maybe, I mean, as per the timetable, I've been given just 1 hour, but I'm trying to, express all those things within your understanding. So now you see, can I say inventory? Now here, how the things get, balanced. So here you see inventory is more, the supply will be increased, right? But if the supply you are keep on increasing, the inventory will be reduced, right? So now you see that this is the anti-clockwise balancing is there. You cannot keep on increasing or keep on accumulation some particular variable, right? So this is how the balancing loops are there, where the positive impact is, the one parameter is giving the positive impact, but receiving the negative impact from the other variables. So that is why the balancing loop exists in the system. So if I give the one more example to you, it is of again same thing, average crop production and the pest in crops. If the average crop production is impacting positively to the pests, oh sorry, if the average crop production is more, pest chances of having pest in the crop will also be higher. If the pests are higher, the average crop production will be reduced, right? So if you see, at one side it is giving the positive impact, on the other side it is receiving the negative impact, right? So this is called the balancing loop. Balancing loop means half positive, half negative. But in reality, you will see it's not just half. It may be 20 positive feedback loops and maybe 200 negative feedback loops. Or the reverse may be there, the 200 positive feedback loops and 20 negative feedback loops, right? But there is always something to balance, and those 20 negative parameters may be having very high impact on the system's performance, right? And that 20 negative feedback loops may be equivalent to 200 positive loops, right? So this is how the system's representation and the insightfulness is very, very important. And the system dynamics modeling is actually helping in that particular goal. Right? So now you see the complete image. These are the causal loop diagram. The state of system itself, in which state the system is now at this particular instant, let us say t equal to t1, how it will be in t equal to t2 or t equal to t3, t4, t5 likewise. So now let us say if I try to understand or uncover the insights of a food supply chain, I cannot be leaving it for T1 to, maybe next 20 years down the lane. As a researcher, I just try to understand what is happening exactly in this particular instance. And then we will predict that what may happen in future with the system if this variable will be keep on changing. So to uncover all the future possible instances, we stimulate that particular food supply chain and we consider all possible variables into our system dynamics model, and we express the relations with mathematical expressions, and then we try to understand that how these two parameters or these set of parameters is interrelated, right? So you see the whole picture is here now. The reinforcing and balancing, both the loops are here. You see production, inventory and supply. These three are the variables. Production inventory cycle is positive cycle, or you can say the positive feedback loop, or you can say the reinforcing feedback loop. On the right hand side, if you see, this is particularly talking about the balancing loop, right? And in this particular balancing loop, you see, it is inventory is increasing, supply will be increasing. If supply is increased, inventory will be reduced, right? So this is how you see how the balance of these two feedback loops is there on inventory. From one side, inventory is receiving a positive input from the production side, but from the supply side, it is getting the negative feedback or negative impact. So this is how the behavior of the inventory variable can be studied. Okay. Then the next example, you see, again the same example I've just combined, and instead of plus and minus sign, I have written R and B. So you see, rainfall is impacting the crop production. Crop production is increasing the rainfall, right? And at the same time, crop production is more is the crop production, more will be the pest. And when more will be the pest, it will be negatively impacting the average crop production. So here in this cycle or in this feedback loop, if you see, the target parameter is average crop production, and you see from one variable it is getting a positive impact, while at the same time the other variable is giving the negative impact, right? So that becomes very important to bring into your notice that what are the exact causes. Though you may see just three variables are there in the picture, and it is very easy to understand. That's why the very easy examples have been introduced so that you can get the idea, right? Slowly we'll apply these concepts into the complex examples as well. So here you see causal loop diagrams, balancing and reinforcing feedback loops exist in the system. Right? Then the question is, how will you identify the loop polarity? You see, some of the tips I've already given, that it's your mental model. You may test it in your simulation model. Then it's your experience. If not yours, others' experience, research papers, books, right? In the experienced people, experts, with this you may get. But when you define the loop polarity, we usually utilize the signum function in the systems. The signum function and the sigmoid function, these two are different. In the sigmoid function, we get the 0 and 1 only. But in the signum function, we get -1, 0 and +1. So the polarity you may identify, if the causality is resulting in negative feedback, we will put it up as -1. If x is -1, the whole function is resulting into -1. If the causality is resulting in positive feedback, we will mention it as +1. And if there is no causal loop, we'll say it is equal to 0, right? Now the next question comes up is that, okay, fine, it is very clear that there are several parameters that in the y is the major target variable, or you can say the major system performance variable, but others, it depends on several other parameters, y1, y2, y3, yn, right? So this is how the cyclic loops may be existing. So now the question is that, how will you identify when it is very, see in this particular previous example, you see it was very simple. One is giving positive impact and another is giving negative impact. and let us say earlier is giving plus 0.3 and the another is giving minus 0.3. So you can be easy, it is easy to identify whether it is overall balancing or overall reinforcing. But in practice, it is not just two variables. Let us say it's a combination of 15, 20 variables. Some are positive, some are negative, some are again positive, some are again negative. So what is the final input or final feedback, right? So what do we do is we keep on multiplying the impact. So now how do we do it? You see in this simple models, rainfall is positively impacting, 1 plus sign. Then again it is giving positive. So you see plus into plus means plus. Positive feedback loop is there, that is reinforcing. But in the next, you see in the next side, you will see one side is it is for giving positive impact, but it is when it is getting back, it is giving negative. Here in this example, it is very simple. In this, just two parameters are there. But just imagine that between these two parameters, there can be hundreds of parameters in between. So how do we identify one causality? We can easily understand that two parameters are there. How one is impacting other? It's all very easy to understand. But the problem is that when there are 15 parameters and all are giving different feedbacks to each other, what will be the resultant? What will be the overall feedback loop, whether it's negative or positive? So identifying that particular thing is really very challenging in the real time or in the real examples. So here you see this particular method is suggested by a researcher, and that I'll be mentioning in the last references slide also. So that particular, I should rather say Jay Forrester has developed this thing. In his book, he has mentioned about this, that how to identify the loop polarity when there are multiple parameters. So you see there are, this particular image is about the multiple parameters. Y1 is impacting Y2, Y2 is impacting Y3 to Y1, and again Yn is giving impact to Y1, right? So it has been suggested that instead of directly trying to make guesses, you better change or better divide or break this loop at some particular point on which you are trying to analyze the resultant polarity. So here you see the Y1i is Y1 input and Y1o is Y1 output. So the loop has been broken down at this particular point. So if I have broken down at the Y1 point, it will help us to understand the overall resultant polarity of the feedback, whether it is positive or negative in this particular cycle. If I would like to understand about Y2, I can break the loop from Y2 into Y2i and Y2o, and then I can identify the resultant. So here you see the polarity is the signum function of input and output, ratio of output and input of the Y1 parameter. And you see how this signum function will be calculated. It will be getting the impact of Y1o with respect to Yn and keep on multiplying up to the Y1i. So you will get that what is the impact I am receiving back. I started giving the receiving the output, what impact I was giving, and then how it is running throughout the loop, and we keep on multiplying all those values, right? And then we'll get the resultant polarity of this particular cyclic relation, or you can say the cyclic loop. This is how the polarity can be identified when there are several parameters in this particular case. Okay. Then the applications of causal loop diagrams. Applications, though by far we but keep on discussing the things together. It is similar to that. You see, visually express the mental model. Then you can apply the causal loop diagrams to understand the communication and feedbacks of the different elements of a system. Then you may utilize these models or these particular causal loop diagrams to express the causality. One limitation of causal loops is that it cannot differentiate whether the variable is a stock variable or not, right? Causal loop diagram just consider a variable as a variable only. They do not distinguish whether it is accumulating or not. So that is why one more type of maps are introduced, stock flow maps. In that, the accumulated or accumulation variables will be visually depicted. And those maps, we mention the flow rate, with which rate the particular variable is increasing or accumulating. Inventory variable, if you see, inventory is something which is a kind of a stock in a company, right? And when you keep on producing, the inventory levels will be keep on increasing. And then if you start selling, so that inventory level will also be reducing. So inventory is basically a stock variable, which causal loop diagrams cannot distinguish. Then the rate of increment and rate of decrement of inventory is, if your production rate is high, your inventory will be higher. If your sales rate will be higher, your inventory will be reducing. So this is how the one more map is there, that is called stock flow diagrams or stock flow maps. So when you try to see that how stock flow diagrams work, as I already explained, that it expresses the stocks or accumulations and the inflow and outflow rates. Inflow means rate of accumulation, outflow means rate of depletion. So this is how the inflow and outflow rates will be considered when we express a stock variable. Okay, so this is how you see we represent the stock flow diagrams, right? So in the stock flow diagrams, these clouds are basically the system boundary, or you can say the source of the flow or input. Then this valve is basically the rate of flow into stock with which this inventory stock is increasing or accumulating, right? Then you see this is the incoming arrow. You see, it is an incoming arrow to the inventory or stock variable, and rate of flow into stock. Okay. Then you see there is an outflow also. Outflow is customer orders, the rate of customer orders basically. More are the customer orders, more will be the reduction in inventory, right? So here you see the important point is to understand these walls are mentioning the inflow and outflow rates with which this stock variable is reducing or increasing. These clouds are basically the system boundary. One is called source and one is called sink. So source means there can be, if I do not mention that who is responsible for production, let us say I'm just try to understand a particular system. Let us say the production of breads. Thousands of factories are there in a city, in a single city, right? And if I try to understand the inventory of breads, right? And all these bakeries which are producing the breads are basically contributing this accumulating variable. If I say this bread production in a particular city, so if I try to understand what is the source, multiple sources, right? And I cannot name all those bakeries here. So I put the cloud sign, which is just the source, right? But when you would like to understand in detail that which factory exactly giving what kind of increment in the bread stock of the city, then you can definitely add that. But here, just to minimize the clutter or just to understand one parameter, we can say that the source is unlimited or very difficult to define. So we put cloud sign, which signifies the source or input source to this particular stock variable, right? Similarly, you see there is one cloud sink. It means which is consuming. So consumers of breads are, it can be anyone, any human, or maybe sometimes it's animals also, right? So you cannot mention all those humans here. It is almost impossible kind of thing. So we say replace it by cloud to show the system boundary and express that it's a infinite sink or infinite source. So we define it using cloud science, right? Then stock variables. How do you represent stock variables? What are stock variables? So you see, we have already seen that A is impacting B. Define. Along with it, there is one more expression, the stock variable. And now here if you say, I'm saying B is accumulating variable. Increasing A will be increasing B. So there is a causality which is existing. But B is the stock variable here, right? Further, to understand more, you see, if I would like to understand the variance in the system between two time T1 to T2, is a huge time span, right? At time T1, the initial stock or initial level of this stock variable B was BT1. And with time, it is keep on increasing. And if it is increasing, so it means whatever is increment in the A, it is increasing the stock variable B also. And the rate of increment is, you see, mentioned here in this expression, right? So it actually shows how do I get this? How can we see this in the real time model, or when we try to develop a simulation, how do we see in the simulated model? We will keep the other variables constant, and by making them constant, then we'll see the only impact of one variable A or one other variable B. And then we'll see that how the stock of B is varying with the changes in A, right? And that expression can be B is equal to BT1, and then it will be adding the rate of accumulation to the stock variable B, right? Then the other side, the depletion of the stock variable, how the depletion can happen. In that, you see, G and E is a accumulation, or you can say the stock variable. And somehow due to G, or G can be a rate with which E is decreasing, right? How it can be expressed. So if E is the accumulating variable, increasing G will be reducing the accumulation of E. And when it is reducing, so let us say initial value of the stock variable was GT1, and with the more G is increasing, E will be decreasing, right? So you see there are two kinds of things involved into it. The polarity, the causality is also involved, right? And then the stock accumulating behavior is also involved. So the stock variables basically express that how or with what rate inflow and outflow rate how the balance is there in the stock variables. So now someone may, may raise a question that, so like this, these variables will be keep on decreasing, or keep on increasing. No. In reality, as I already explained, there may be thousands parameters, right? Some parameters may be impacting positively and some may be negatively. So this is how we model our system dynamics models, right? Okay, so by now we understood what are the variables, how they're related, what kind of relations are there, right? Then we talk about mathematical relations. How do you express those mathematical relations between two variables or more than two variables, right? So mathematical expressions are the basic requirement because the variation of those two or multiple parameters will be governed by their mathematical relation. If you just write two variables and write a plus sign, you will not be able to change, or you will not be able to see any change with respect to time. Those two will be kept on constant throughout the simulation process, right? And with time, there will be a horizontal line, no change at all, because you have not related them mathematically. So change in one, how will that, it is something, y equal to x plus c. We usually understand that if x will be changing, the right hand side of the equation will be changing, then only the y may be changing. So if you want to see the change on the y, or you can say the dependent variable, you have to modify the independent variable all throughout the process, right? So this is how we always try to express that what kind of behavior with which they are related, right? Linear, quadratic, or maybe just a constant or whatever, right? We'll see some examples. All the variables which are defined in a system should be related. If you put some variables in the model, visual model, but you do not define the mathematical expressions, there will be no change in the simulated models, right? And you will not be able to see any change while performing the sensitivity analysis also. Then the next important parameter is initial time and initial value, especially in the case of stock variables. You have to mention that what was the initial stock and at what time, so that you can understand that as the time is progressing, how the stock values are changing, upgrading or degrading or whatever. Okay. So mathematical models can be created based on existing research, historical records, personal experiences, and your mental hypothesis, what kind of thought process you are having, right? So this is how we define the mathematical relations, without which there is no standard way, but the relation of two variables can be identified by closely monitoring them. Okay. And you may change the equations as well. Let us say today you have considered the relationship is linear, but with experience you may find that no, it is much higher, it is giving much higher impact. It should be quadratic, or it should be something, different. So like that, you may keep on improving your mathematical expressions. The more you are making it robust, the errors of the model will be much lesser than the expectations. And when the models are having lesser errors or more robust, it will be replicating the reality so well, right? So you see this example of system dynamic model for a steel bar production. This is from one of my research work. So there we studied the steel bar production and how it is, getting impacted by different variables. Now you see this simple research model and how complex it seems, right? So I'm just showing you one very simple example, right? I hope you are able to see my screen. Yes. Okay. So you see, there is a one simple variable, available chocolate stock. So here I'll be showing you two differences, that how the causal maps do not consider this, accumulation or stock variables. So here you see available chocolate stock is basically a stock variable, right? But the inflow and outflows are not defined because it is just a simple causal map, or you can say, yeah, simple causal map. Purchase rate will increase, the higher will be the purchase rate, higher will be the available chocolate stock. Then if the chocolate stocks will be higher, more chocolates can be given to the kids. Right? If the school, now the consumption rate, one side we are talking about purchase rate, another side we are talking about the consumption rate. One is increasing the stock and the consumption rate is negatively impacting the stock of chocolates in the school, right? And then you see what are the other parameters which are impacting the consumption rate, number of kids in the school, and then the school duration, right? Very simple model, just you can say, just to illustrate that how the causal map or causal feedback loops do not consider the stock variables. It is just simple. Then with time, let us run the simulation. You see, as I am increasing the purchase rate, how the available stock is increasing with time, right? So here you see, when I am moving this, nothing else is moving. Or nothing else means other dependent parameters. I fix those parameters. You see, there is no change in the school duration. There is no change in the number of kids in school. I'm just changing the purchase rate. And when I'm changing the purchase rate, you see, the stock is increasing or decreasing. So this is how I could recognize that what is the impact of purchase rate in the stock variable, right? And then if I try to understand the school duration, if the school duration is changing, the consumption rate is, you see, is increasing, right? So this is how we can analyze. This is called the sensitivity analysis, where we express that how exactly things work, right? So what I defined so far is just a small example to understand that how things are happening. Now you see one more complex model I am showing to you. In this model, if you see, it seems, you see, this is a model. I have developed all these models on Bensim. You may also try. It's a free ware, so it is applicable for free to any of the user. Right? Though there are multiple softwares in the domain, you may utilize any logic and then the MATLAB. In MATLAB is or you can say MATLAB is just one software forum where you can do several kind of mathematical and simulation analysis, right? So you may always utilize the MATLAB tool or the AnyLogic, VenSim, then there is PowerSim is also there, but I have not used many software so far. So one is AnyLogic and there is VenSim, which you can utilize very easily, right? So here you see in this particular model, let us run the simulation. You see there are multiple parameters, multiple feedback loops are there, reinforcing loops, feedback loops, right? And it's not only just one, there are many. Okay, and then if I run the simulation, you see all those parameters, you see the change. If let us say I'm changing this just one variable I'm changing, and then it will show the changes in this whole, especially the steel bar production. So let us say I'm just changing the maintenance policy. Is not giving much change, but let us say one parameter which I can change is reinvestment ratio. So let us see that if I'm changing the reinvestment ratio, you see all these lines are there. I hope you are able to see these lines. So please, you see these lines, these are the curves. These are the curves that how with the time things are changing, right? Or these variables are changing. You see, simulation is still running. So it is showing that how the parameters or variables are keep on changing. And then you see there is a steel bar inventory, which is the main variable in this particular study. So though this is a working model, we will be developing more things with time. So here you see that if I try to change the reinvestment ratio, you see how all these bars or all these graphs are changing. So it will help us to understand that what is the role of this reinvestment ratio in this particular whole steel bar production system, right? I'm changing just one variable and I'm trying to analyze its impact on the all other variables, right? Similarly, if you see, let us say I would like to change the grade of the steel. So with grade, there is no change in the production or in the inventory, right? So this is how with the time we may see the different kind of parameter changes and we can define the variance in the system, right? So this is how we can always define some particular parameters in the models. Okay. So I could just show you some particular models at a glance, though these are not the detailed, working of the models. Considering the time constraint, I'm bound to, to finish the module in just 1 hour in module 3, right? So with this, our module 3 will be closed. But if you would like to understand it more, you may try your hand on different software, or you just take some small example around you, right? That electricity consumption, right? Or the students' admission in the institute, or some any other variable which you are thinking that it may be very important to the society or an organization, or any particular institute or any particular engineered system. You may take this up and then you may try to model on your own. You just first try to bring your mental model or the hypothesis which is have you are having in your mind. You can develop a visual model first, and then you may keep on experimenting, and then you will find that a point will come that you will be able to uncover the whole system dynamics, right? So that is the major takeaway of this particular module. So with this we are completing module 3, and in addition to the discussion of today's class, I would like to discuss the references and further readings. So, as I already told that J. Forrester was the pioneer who developed the system dynamics modeling. In 1987, he published, a book, and then the J. Forrester himself, he kept on defining it more and more. And then later on, there is a Professor Easterman, and he again wrote down a book. It's a huge book, maybe more than 1,000 pages are there in that book, and that book is very exhaustively showing everything in detail. Very minute details he has covered in his book. So I prefer these kind of books you should go through to understand how the things are happening, what is the role of each particular thing, what I have expressed today. Then there is one more book on system dynamics modeling by Cole, right? And then last but not the least, there is a system dynamics society also. And in that society, you can find out many sources for system dynamics modeling, multiple softwares, and multiple tutorials and lessons are available over that. To conclude, the list of softwares to develop your own SDMs, you may utilize WenSim, PowerSim, MATLAB, and AnyLogic, right? So I think now you are very clear with the role of systems dynamics, right? And how the variables can be listed and analyzed within a particular system. So for further discussions, I'll be available after the sessions. So you may talk to me. Okay. So thank you so much.